So far, we have seen several types of geometric relationships that can exist when two linear equations are simultaneously graphed. Simultaneously graphing systems of equations like this is often a helpful tool in analyzing physical and mathematical relationships. In particular, the points of intersection of two graphs have a special significance, since the intersection points represent common solutions to both equations. To illustrate this concept, let's look at a race between a tortoise and a hare. As the race begins, the hare, engrossed in a fascinating chapter in his algebra book, decides to give the tortoise a head start so that he can finish reading the chapter on solving systems of linear equations. As the race begins, the tortoise starts down the road at 1/2 mile per hour, a very brisk pace for a tortoise. We can graph the tortoise's distance from the starting point as a function of time, letting the vertical axis represent distance and the horizontal axis represent elapsed time. We see that in the beginning, when the elapsed time is 0, the tortoise's distance from the starting point is also 0. After that, since he is traveling at a constant speed, his distance increases linearly as a function of time. Since the tortoise's speed is 1/2 mile per hour, after 4 hours, he has traveled 2 miles. 4 hours after the race has begun, the hare finally finishes his algebra chapter. Even though the tortoise has obtained a significant head start, the confident hare decides to take it easy. Since he knows that even casually strolling at 2 miles per hour, he will eventually pass the tortoise. So 4 hours after the race has begun, the hare is still 0 miles from the starting line. But from this point on, he travels at a constant speed of 2 miles per hour. Since the hare travels at a faster rate than the tortoise, the hare's graph has a greater slope. Looking at these two graphs, we see that throughout the race, the tortoise's distance increases linearly with time. And after 4 hours of elapsed time, the hare's distance also increases linearly. Until at some point, between 5 and 6 hours after the race has begun, the hare and tortoise meet. The point where the two graphs intersect represents the instant at which the tortoise and the hare are at the same place at the same time. If we can create equations for these two graphs, there are mathematical techniques which we can use to determine the coordinates of the point where the two graphs intersect. Knowing these coordinates, we can then determine the exact time and place where the tortoise and the hare meet. To create an equation for the tortoise's distance as a function of time, let's use the variable x to represent the time coordinate and y to represent the distance coordinate. We saw in the chapter on solving motion problems with linear equations that if we graph distance as a function of time for an object traveling at a constant speed, the slope of the graph will be equal to the speed of the object. So the slope of this line is 1/2. Since we know that this graph intercepts the y-axis at the origin, we can use the slope-intercept form to write the equation for this line. The value of the constant m in this equation is the slope of the line 1/2, and the value of b is the y-intercept 0. Eliminating the 0, we see that the equation for this line is y equals 1/2 x. Now that we have the equation for the tortoise's graph, we need to derive the equation for the hare. Since the hare is traveling at a constant speed of 2 miles per hour, the slope of his graph is 2. We don't know the line's y-intercept, but we do know that the line passes through the point 4, 0. So we can use the point-slope form to write the equation for this line. Filling in the values for the constants, we replace x1 in the equation with 4, y1 with 0, and m with the line slope 2. We can then simplify the equation by eliminating the 0 and distribute the 2 to the terms in parentheses. Multiplying 2 times 4 to get 8, we see that the equation for this line is y equals 2x minus 8. We now have equations for the tortoise's and hare's distances as functions of time. It is important to remember that although the lines described by these equations extend infinitely in both directions, only the portion of the lines whose coordinates are positive are meaningful in this particular example. If we can now use these equations to calculate the coordinates of the point where the two graphs intersect, we will be able to determine the exact time and distance where the tortoise and the hare meet.